All right, so we are going to continue from where we left off with topic 4.2 isotopes. And so again, you're going to want to make sure that you have your periodic table, calculator might be useful, and even yesterday's notes might be handy as well. So we're going to talk about isotopes and basically how can two atoms of the same element be different from one another. This is going to become important as, like I said, we're going to make our way towards nuclear chemistry. And so the thing to understand is an isotope is an atom of the same element. Again, what makes them the same is that they have the same number of protons. Again, that's the only particle truly responsible for identity. But what they can differ in is how many neutrons they have. And then if your neutrons are changing, that can give you different mass numbers. So like I just mentioned, right now for where we're at, atoms of a given element have the same number of protons. That's always going to be true. But electrons don't, and we're going to talk about how that can change as well. But that's, again, for today, we're just going to keep it that they are equal with that particular neutral element or atom. However, an atom does not have to have the same number of neutrons. So for hydrogen, for example, there are 3 different isotopes of hydrogen. The one characteristic they have in common is their atomic number or protons, but what varies in them is how many neutrons they have. Okay, and so when those neutrons vary, that decides if something's going to be stable or unstable, and then again, will it undergo radioactive decay to become stable. So here we have 3 particle or Bohr models. Again, not the best representation of an atom. However, it does make it easier for these first units to use Bohr models. So the first thing we're going to do is count particles, because that's what we can do right away, and then we can go in and get the rest of the information. So looking here at this first example, it wants to know how many protons you have. If you remember, protons are positively charged, so these yellow ones with the plus are representing positive charge, and so we have 6 of those. Neutrons are found in the nucleus, so we have these 6 fuchsia-colored spheres, so that's 6 for that. And then electrons, there are negative charge, so there's 4 across, 2 up, so this is 6 as well. So if you remember, protons and atomic number are what are lassoed together, so the atomic number is 6. Mass number is your protons plus neutrons, so we have 12. And so what's the name of the element? The only thing that's going to tell us that is the number. And so if you go to your periodic table, you will discover that this is carbon. So for our next one, and you could also just write the symbol C, either one's fine. So for example B, same idea. We have 1, 2, 3, 4, 5, 6 protons as well. And now in this case, we now have 7 neutrons, but electrons are still 6. So that means the atomic number is still 6, but our mass number is now changed. We add these 2 together, so we now have a mass number of 13. But because protons are the same, giving us the same atomic number, we are still talking about good old carbon. From example C, count that up. We now, again, have 6 protons. We now have 8 neutrons, and we still have 6 electrons. So atomic number is 6, mass number is 14, and again, we have carbon. So then it asks us a couple of questions about what's the same and what's different. So using your table, you can make some comparisons. So these are what are called isotopes. So they are all of the same identity. So my way of thinking of it is these are like ice cream. But when you go and buy ice cream, you can buy different flavors of it. But it's all, at the end of the day, ice cream. So these are all carbon. They are essentially different flavors or different isotopes from one another because of their neutrons varying. So what's the same about them? Well, there's a lot of different things we can say. So we can say that the atomic number, protons, and electrons are the same. What differs about them then? Their mass number is what's different about them, and that's because their neutrons vary, okay? So because we have isotopes, we have to have a way of representing them. So I'm going to teach you 2 different ways to represent them. One is called the hyphen notation, and the other one is nuclear notation. So with hyphen notation, there are 2 parts to it. let me change my pen color. That might show up just a little bit better if I maybe write in white. So here, hyphen notation, the two parts that it has is the name of the element followed by mass number. So it tells us in practice 1, we're figuring out protons, neutrons, electrons based on this hyphen notation. So we know that the name of the element's hydrogen and that its mass number is 2. So to do protons and electrons, we would then use our periodic table, finding the atomic number. Hydrogen is atomic number 1, so 1 proton, 1 electron. So for neutrons, we get that by taking the mass number, so that's given to us here, this number 2, minus our protons, so this one has 1 neutron. So in carbon 14, what we again know is the name of the element, so let's figure out its atomic number using the periodic table. You would find that it's atomic number 6, meaning it also then has 6 electrons. Again, to do the neutron part, you take the mass number minus protons to give you 8 neutrons. So it's using that same skill from topic 1, except using it in hyphen notation. So now I give you some parameters and we're going to write the hyphen notation based on what I give you. So in letter A, I tell you that this isotope has 6 protons and its mass number is 12. So you need to figure out the name of the element, and so you do that from protons. That's the same thing as atomic number. So going to the periodic table, that is carbon. Again, after the hyphen is always your mass number, which in this instance, it's directly given to you. So this is the isotope for carbon 12. In example B, the atomic number is 6, and it has a mass of 13. So atomic number is equal to protons. So again, we have carbon here. So we have carbon dash our mass number, which again was directly given to us, 13. And then this one has 6 electrons, 8 neutrons. That tells us that this is also the protons. And then that means, again, that is our atomic number. So yet again, we have carbon, hyphen its mass number. Mass number wasn't given to us here, but if we add up protons, being 6 protons, to the 8 neutrons, we get carbon 14. So these are the hyphen notations for those 3 Bohr models that we broke down in the top part of the notes. So it's that same information, again, just different ways of representing it. The other format that I want you to be comfortable with, and this is going to be the one we use the most, is what's called nuclear notation. And this is kind of like the density equation where we're just plugging things in. So what we have is, this is like our formula. We have A, Z, and X. So if you take a look, X is where you would write the symbol for the element, A is where the mass number goes, and Z is where the number of protons go. So what we're going to do is take these 3 and translate them from hyphen notation into nuclear notation. So the first thing I do is we're going to put in our symbol. So using the periodic table, if you don't know it, the symbol for carbon is an uppercase C. Now, for format, you always write your mass and atomic number on the left side, and in the upper left, this is called the exponent, or what we call superscript, is the mass number. That's this piece of information here. So that's 12. In the lower left corner is the atomic number. That's not given to us, but we can use the periodic table. It is a 6. This is not the correct format. We're not writing a fraction, and you do not write it on the right-hand side. It has to be set up this way for format when we get to nuclear decay. So moving on, we have fluorine 19. If you don't know the symbol for fluorine, you're going to find that it's an uppercase F. The mass number is given to us, so we substitute that in the upper left corner is the superscript. And then looking at our periodic table, the atomic number of fluorine is 9. This last one, beryllium 9, if you use your periodic table, beryllium is Be. Mass number is 9. Using our periodic table, you'll find that it's atomic number 4. So this is how you go from hyphen notation into nuclear notation. Practice 4, we're going through and I give you parameters and you're going to go ahead and figure out the element's identity to then fill in the rest of the info. I tell you the atomic number is 3 and its mass is 7. So I can go ahead and plug that information in. Mass is 7, atomic number 3. When I look at my periodic table, The element that's assigned atomic number 3 is lithium, which is uppercase L, lowercase I. For this next one, I know particles, protons, and neutrons. So to get mass number, my upper left number or my superscript, I need to add these two together. So 92 plus 146 is going to give me 238. Lower left or my subscript is protons. That's 92. If you take a look, 92 is in the part of the periodic table that's cut out. So if you go all the way to the bottom, you will find that it's uranium, which is an uppercase U. Here we have a mass number of 14 and 7 electrons. So mass number is given to me, so I can substitute that in. If I have 7 electrons, we have 7 protons. Using my periodic table, the element assigned atomic number 7 is nitrogen, which is N. The last one, and I'm going to change my pen color so it shows up, is it's asking which two are atoms of the same element. So the X doesn't represent anything. It could be any symbol. So what you're looking at is, and you have to understand, is how are they the same element? So mass has nothing to do with if they're the same element. So A is not a pair of the same element. Mass number is the same, but the part that we care about is the atomic number or protons, and that's not the same. In letter B, we have different mass numbers, but we have the same atomic number. So B would be an example of an isotope. In this next one, they are not isotopes of one another. None of the numbers match up, even mass or atomic. And then last one, same thing. So the last part here is we have a table. I'm going to fill out a couple of these, and then I would recommend pausing it and seeing how you can fill it out on your own. So in this first one, I give you the nuclear notation that we have 65 over 29 and Cu. So the atomic number is that lower number. So 29 is our atomic number, and that's kind of an awful shade of orange. So let's try something else out. Let's try purple. So then we have mass number. That's my superscript of 65. How many protons does it have? So that's going to be 29. And we can do electrons, 29. So then the number of neutrons, we're going to subtract these out, and we get 36 by subtracting 65 and 29. Hyphen notation then. So you can do hyphen notation two different ways. So you can do it this way where you write out the full name, hyphen mass number, or you can also do it symbol, hyphen mass number. Either one's fine. So in the next column, I tell you that we have an atomic number of 5, and I tell you that it has 6 neutrons. I can figure out mass number right away by adding 5 and 6 to give me 11. Atomic number is 5, so 5 protons, 5 electrons. Now we need to write our two notations, so we need to figure out what it is. Using our periodic table, atomic number is 5 is boron, or B. Superscript is going to be 11. Subscript is going to be 5. For hyphen notation, boron, or B-11, always followed by mass number. So in this next one, it's not a typo. I only tell you that it's 86 and Kr, or krypton. So you can fill in this last piece using your periodic table. If you find krypton, it's all the way on the right-hand side of your periodic table. Its atomic number is 36. So that's 36 here and 86 here. From here on out, as you fill out the rest of this, you have 36 protons. Subtracting 86 from 36, you get 50. We have 36 electrons because of the 36 protons. And symbol for krypton's Kr, hyphen 86. I would recommend that you take a minute now to pause the video and fill in the last 3. All right, hopefully you took my advice and you paused it. So we have atomic number 78 here and 117 neutrons. So you should have got 195 for mass number, 78 protons, 78 electrons. You would find that this is platinum, or PT, 195, 78 for the subscript, PT hyphen 7, or not 78, 195. Here you had 46 neutrons, 36 electrons. So that means there's 36 protons. Atomic number is 36. Adding protons and neutrons, you should have got 82. So you have 82, 36, and we have krypton again, Kr-82. So these are isotopes of each other. So they're the same flavor, they're the same element, different mass numbers. Gold, if you use your periodic table, be careful. It's not AG, but it's AU. You have the number is 198, and looking at your periodic table simultaneously, you should have discovered its atomic number 79. So that gives us protons and electrons. Mass number was provided. Subtracting those two out, you get 119 neutrons. So we're using skills from topic 1, but now continuing to add it for our notations to represent isotopes. If you have any questions about where I got some of this information, or if you're needing a hand, let me know. Otherwise, go ahead and work on your homework.